Welcome back. Today we are going to push beyond polynomials and figure out what the derivatives of sine and cosine are. Our approach is going to be a little bit different this time because if we try to find, say, the derivative of sine x by appealing to our first principles recipe for derivatives, everything looks fine at first. Hopefully you remember that there is an identity that allows us to expand the sign of a sum. And if we were to apply that here, we would get all of this stuff. And now we see where the trouble lies. What are we supposed to do with expressions like cosine of dx or sine of dx? What on earth are we supposed to do from here? We seem to be stuck. There actually is a way to make sense of expressions like these, but it would take us a bit too far afield. So what I'm going to do is back up and try a totally different approach, an approach that isn't just following a recipe, but goes right to the heart of what this sine function is in the first place. It will be a very geometric proof, and a very beautiful one. But before we figure this derivative out by this geometric proof, I want to remind you of just a few basic geometric facts that we'll need during the argument. This way we won't get bogged down in the middle of the argument. First geometric fact. If we have a circle and a tangent line to this circle, then the radius that touches the tangent line is perpendicular to the line of tangency. You've seen this already in the exercises in the book, and it's a fact that I'm sure you're very familiar with from geometry or trigonometry classes, because this gives us a way of bringing right angles into problems about circles. And of course, where there are right angles, there are right triangles, and therefore there is trigonometry. So that's the first thing I wanted to remind you of. The second is that if we have a circle of radius r and a central angle alpha that cuts off some little bit of arc length, then there is a very simple formula for the actual arc length in terms of r and alpha. And it's especially simple if alpha is measured in radians. Hopefully you remember the formula I mean. It gets used all the time in geometry where there are circles, or for that matter in physics where you might be describing things like circular motion. But in case you've forgotten it, we can derive it in about 2 seconds. This bit of arc length is some fraction of the entire circumference. And the circumference, of course, we know is 2 pi times the circle's radius. Now, I said this arc length is some fraction of the whole circumference. Well, what fraction is it? Well, it is the same fraction of the whole circumference as this central angle is of the whole full angle. Well, what fraction of the full angle of 2 pi is alpha? Well, there's nothing deep here. That's just alpha over 2 pi. And notice this is where I am using radians. If we were doing this in terms of degrees, this would have to be alpha over 360. Anyway, this will give us the arc length. But when I simplify this expression, the 2 pi's cancel, and we're left with just an r and an alpha, which means that this arc length is going to be r alpha, the product of the radius and the central angle. Okay, with those preliminaries out of the way, let's figure out what this derivative is. In fact, since I'm going to be emphasizing the geometric meaning of sine, let me make the independent variable, instead of x here, let's call it theta. That way, when I'm drawing pictures, I can label my angle theta instead of x, which feels a little unnatural somehow. All right, so this is supposed to be our unit circle, which is hardly a surprising thing to show up when we're thinking about sine, because sine is defined in terms of the unit circle. As you remember, of course, if we start with a point here at 1, 0, and we rotate around through an angle of theta, then the coordinates of that point are cosine theta, sine theta. That is how the functions cosine and sine are defined on the unit circle. So if I were to drop a perpendicular here, since the first coordinate of this point is cosine, this length right here would be cosine of theta. And since the second coordinate of that point is sine of theta, well, this length right here would be sine of theta. Okay, so far so good. But what does this have to do with derivatives? A derivative is a rate of change. It tells us how this function, in this case the sine function, changes with respect to little changes in its input variable, theta. Well, we can relate this idea to our figure because I have a visual representation of sine's output right here. It's the height of that triangle, or more properly, it's the second coordinate of that point as it moves around the circle, and I have a visual representation of the input of the function, theta. So I can think about on this picture how the output changes in response to changes in the input. But of course, it's not just any old rate of change, it is an infinitesimal rate of change. It is therefore a ratio of infinitesimals. So let me rewrite this accordingly. We can figure out what this is by thinking hard about this figure right here. Our figure has theta and sine theta in it, but what it does not have are the elements of my ratio here. It doesn't have d theta, the infinitesimal change to theta, and it doesn't have d sine theta, the resulting infinitesimal change to sine's output. But I can draw them in here, at least in a schematic drawing. Obviously, I can't draw infinitesimals, but we can draw something that will help us think about them. Start with d theta. That's an infinitesimal change in theta, a little infinitesimal increment, a little nudge to this angle right here. We're going to increase it just a tiny bit more to theta plus d theta. Well, if I pack on just another d theta in there, it will increase the angle ever so slightly. Now again, I can't draw an infinitesimal angle. As you can see, I can't even draw a straight line very convincingly, but it's just a schematic picture, and we can still reason with it. So let me try to draw that in here. So here's my angle theta, and here's a little infinitesimal more, d theta. Now when I make that change, when I increase the input ever so slightly, I get a corresponding change in the function's output, because when I increase the angle, of course this point moves up the road a little bit. It moves from here to here. So its second coordinate changes. It's increasing. In fact, it's changed by this little amount right here, the edge of that tiny right triangle. That's actually an infinitesimally small right triangle. And that leg of it represents the change from the old value of sine when the input was theta to the new value of sine when the input was theta plus d theta. So that leg of the triangle is d of sine theta. That is the infinitesimal change in sine theta that was produced by changing the input from theta to theta plus d theta. Good. And notice that these two new pieces that I've put in blue are exactly the pieces in my ratio that I'm looking for. If I could find some way to bring them together, then I'd be in business, and I might actually be able to learn something about their ratio, thereby determining the derivative of the sine function. Well, that's easy. Remember the second of the two geometric facts I reminded you of. This little arc length that I've drawn in red. What is it? Well, we said that an arc length on a circle is the product of the circle's radius and the central angle that it cuts off. That means this arc length has to be 1 times d theta, or in other words, it is d theta. So now I have the two pieces of my ratio of infinitesimals I want, and they're on the same triangle. Here's d sine theta, and here's d theta. This is good, but what am I going to do with them? I need to figure out something about their ratio. What can I say about the ratio of this side of my infinitesimal triangle to this side of my infinitesimal triangle? I keep calling this thing a triangle, but you might say, yeah, but one of the sides is curved. It's not really a triangle. It is, though, since it's infinitesimal. And on an infinitesimal scale, curves are straight. I can't draw it perfectly straight, of course, because I can't draw infinitesimals. But I have to think of this thing as a tiny, tiny, infinitesimally tiny right triangle. Anyway, I have this ratio of sides on that right triangle. Ratios of sides on a triangle should make us think of similar triangles. If I can find another triangle that is similar to this one, then maybe I can use something about similar figures to say that this thing is equal to something not involving infinitesimals, which is what I want ultimately. Because I want to say the derivative of this real function sine is some other function that doesn't involve infinitesimals. Well, let's see. Might there be a triangle similar to this one hiding in plain sight? There is. It's this right triangle. Now, how do I know that these two right triangles are similar to one another? That's a big claim. Well, as you remember, one way to show that two triangles are similar is to show that all their angles are the same. Certainly, both of these triangles have a right angle. That's a good start, but we need to show that their other angles are also equal. How am I going to do that? This shouldn't just be a matter of faith. This is where that first geometric fact that I reminded you of is going to help us. I've redrawn this part of the figure over here just to try to avoid some clutter. It should help us with our reasoning a bit. Anyway, the goal is to prove that these two right triangles are similar to one another. Well, the easiest way to see this is going to be to extend this infinitesimal bit of arc length. It's infinitesimal, so it's part of a straight line. Namely, it is part of the tangent line drawn to the circle at that point. So let me draw that over here, like so. Since this red line is a tangent line to the circle, and this is a radius of the circle, then this angle right here is a right angle. Okay, that's good, but why does it help us? Well, think about this angle right here in this big right triangle. Let's give it a name or a symbol. How about the purple dot? So my big right triangle has, besides its right angle, its two acute angles, theta and the purple dot. So theta and the purple dot are complementary angles. They add up to a right angle, because I know that in any triangle, all three angles have to add up to two right angles, and we've already used up one. Okay, so theta and the purple dot are complements. Their sum is a right angle. But now look at this right angle that we have right here. It's made up of the purple dot and whatever angle this is. So the purple dot plus this thing is a right angle. That means this thing is the complement of the purple dot. But I already know that the complement of the purple dot is theta, so I can label this angle theta. Aha! As everybody knows, if two lines cross one another, then the so-called vertical angles across from each other on the vertex are equal to one another. Well, look at this picture right here. We have this line and the red line crossing each other. That means these vertical angles, this one and this one, are equal to one another. That means this angle in the little infinitesimal triangle must also be theta. And now I'm really glad I did not try to draw all this stuff over here. Good. So now I know another angle in my infinitesimal right triangle. And while I'm at it, what's this last angle in the infinitesimal right triangle? Well, it's going to be whatever I have to add to theta and a right angle to get a full 180 degrees. But I know what that angle is. Just look at the big triangle. The sum of the angles here is 180 degrees, and it's theta and the right angle, and the leftover stuff is the purple dot. So in this corner, I will also put the purple dot. And now we can see that these two triangles really do have the same angles, and therefore they are similar to one another. Hooray! And of course, we like similar triangles because corresponding ratios on the triangles are equal to one another. So this ratio we're looking at over here, d of sine theta over d theta, I can read that ratio off on the little triangle. d of sine theta, that's the side opposite the purple dot, and d theta is the hypotenuse. So the same ratio over here is going to be equal to this thing. Well, opposite the purple dot here is cosine theta, and the hypotenuse is 1. So that means if I come back here, I can get rid of this question mark, and in its place put cosine theta over 1. And again, this equal sign is justified by those similar triangles. And of course, cosine theta divided by 1 is better known as just plain old cosine theta. And we've done it. We have found the derivative of sine theta, and it's as nice as could be. It's cosine theta. All right, I hope you enjoyed that argument. Let me compress this a little bit, and there is the famous result. Now, I promised you the derivatives of sine and cosine. We now know that the derivative of sine is cosine, but what about the derivative of cosine? Might it be sine of theta, or might it be something else? We'll have to find out. And you might be wondering if we're going to have to repeat a whole complicated argument like this to do so. Not really, because we've done 90% of the work already. After all, our original picture has cosine theta and theta on it, and in fact it's got d theta in two different places now, but it doesn't have d of cosine theta. So you might think, aha, I see it already. It's going to be this side of the little infinitesimal triangle. Almost, but not quite. There's one thing we have to take account of. This side of the triangle is a length. An infinitesimal length, I grant you, but a length. That means it has to be positive. However, the infinitesimal change in cosine theta is not positive, because when we make that change, the value of cosine gets smaller. That means this is a negative change. So I just have to take this and switch its sign to get the side length of that triangle. So that side will actually be the negative of d cosine theta. I'll bring that over to our triangle over here as well. There it is. Now, we're looking for the derivative of cosine, which is, of course, d cosine theta over d theta. And you might be a little dismayed to see this negative. How are we going to get rid of it? Well, we'll just keep it in there for now, and we'll do a little bit of algebra afterwards to get rid of it. The important thing to recognize from the similarity of these two triangles is that minus d of cosine theta over d theta is a particular ratio of sides. It's the side opposite theta over the hypotenuse. Well, thanks to our similar triangles, we know that we can look at the corresponding ratio over here. The side opposite theta is sine theta, and the hypotenuse is 1, so this ratio becomes sine theta of 1, which is, of course, equal to just sine theta. Well, let me compress this a bit by eliminating that middle term. Okay, there we are. Well, this is almost what we're looking for. Let's just take this equation and multiply both sides by -1 so as to get rid of that negative out front. When we do that, we end up with d of cos theta over d theta is negative sine theta. And of course, this is the very thing we seek. It is the derivative of cosine theta. And so we have what we were looking for. The derivative of cosine theta is not quite sine theta, it's negative sine theta. So we'll put this in our sack. And we have both of the derivatives we were looking for. Excellent. And of course, the independent variable doesn't mean anything. The thetas here, this would hold if we had x's or q's or z's or whatever you want. The derivative of sine z is, of course, just cosine z. The derivative with respect to smiley face of cosine of smiley face is minus sine of smiley face, and so forth. The variable is just a dummy variable. If you take the derivative of sine or cosine with respect to whatever the dummy variable is, you know what you're going to get. And of course, these specific results, these derivatives of these two specific functions, are more grist for the mill of our structural theorems, such as the linearity properties we learned last time. So for example, if we had a function like this, 3 sine x plus 5 cosine x minus 2x squared, we could find its derivative very easily, because it is built up of 3 terms whose derivatives we know. One of the linearity properties we proved last time tells us that the derivative of a sum is the sum of the individual derivatives. And each one of these individual derivatives are easy because our other linearity property tells us that constant multiples like 3, 5, and minus 2 can be pulled through the derivative operator, like so, leaving us with the derivatives of bare functions whose derivatives are well known to us. The derivative of sine is cosine, the derivative of cosine is minus sine, and the derivative of x squared is 2x, which combines with this to give us minus 4x, and we are done. I wrote this out very carefully, but in practice, after doing a few of them, you should be able to just look at this thing and write down immediately that the derivative is 3 cosine x minus 5 sine x minus 4x. One more thing. If y is sine x plus cosine x, then the derivative of y with respect to x is clear. It's cosine x minus sine x. I don't think that will cause anyone any trouble. However, let me change this function a little bit. Suppose y is sine x times cosine x. There are, alas, many Calculus 1 students who would try to claim that the derivative of this function is cosine x times minus sine x, because those are the derivatives of the corresponding factors. Is this true? It is not. Please do not do that. Things are true in mathematics for reasons, not just because they feel good. It would feel great if that was the derivative. But we don't have a theorem telling us that the derivative of a product is the product of the derivatives. In fact, the derivative of a product is not the product of the derivatives, as we'll discuss more in the next lecture. But it actually turns out that we can find the derivative of this thing even before we know the product rule by using a neat trick that you should know about. Before I show you the trick, I want to start by just massaging this thing into a nicer form. If you've learned trigonometry well, this expression, sine x cos x, should be lighting some neurons up in your brain. It looks very similar to something that occurs in one of the most basic trigonometric identities, namely the double angle identity for sine. In case you've forgotten it, that identity tells us that the sine of 2x is 2 sine x cosine x. This should be as familiar to you as 2 times 3 is 6. If it isn't, make it so. And while you're at it, don't forget the double angle identity for cosine, which tells us that cosine of 2x is cosine squared x minus sine squared x. These double angle identities come up all the time, so do yourself a favor. If they are not already firmly embedded in your head, get them in there tonight. Say them 100 times, whatever it takes, but get them in there. Once they're in there, the expression sine x cosine x should make you think of this double angle identity for sine, because sine x cosine x is a prominent part of it. It is half of the right-hand side, which means that it must be half of the left-hand side. So I can say that this expression right here is equal to half of sine 2x. That's a little nicer. And at this stage, you might be tempted into making an understandable mistake. You might be tempted to think that dy dx is half of cosine 2x. This, however, is not correct. The problem here is that this function, sine of 2x, that is not just the sine function. This is the function that takes its input, x, doubles it, and runs the result through the sine function. That's a composite function. we don't know the derivative of that twofold function. We only know the derivative of the sine function that just takes the input and gives you back its sine. So this feels right, maybe, but it isn't quite right. As I say, an understandable mistake, but a mistake nonetheless. Still, there is a way to come up with this derivative, which I'll show you now. The trick is to unpack this composite function, to rewrite it explicitly in two stages by introducing an intermediate variable. We'll say this stuff is half the sign of a new variable u, where u is just standing in for 2x. So what we have done is we have taken our original function, where we have y as a function of x, and we've introduced this new variable u, so that now we have y is a function of u, which itself is a function of x. And while we are ultimately interested in finding the derivative of y with respect to x, we'll do it in two steps. That's what the u allows us to do. We'll use it as a kind of stepping stone. We're looking for dy dx, but what I can do is I can factor this derivative into two simpler derivatives. We can rewrite it as dy du times du dx. This equal sign holds by just ordinary multiplication. The factors of du cancel, and we're left with dy dx. Anyway, how does this help us actually compute the derivative? Well, now it's easy. Take one piece at a time. What's dy du? The derivative of y with respect to u. Well, here is y as a function of u. I know how to take that derivative. That is going to be half of cosine u. The half just sits there because it's a constant multiple, and the derivative of sine u with respect to u is of course just cosine u. But now I have this other factor, du dx. What's that going to be? Well, here's u as a function of x. U is 2x. What's the derivative of this function with respect to x? Well, of course, it is the constant function 2. And now this half and the 2 cancel out, and I'm left with cosine of u, which looks pretty simple, but the u is just a bit of scaffolding that we introduced into the problem. We need to take it down and write the answer in terms of the original variables. We started off with y as a function of x, and we're looking for derivative of y with respect to x. So I can't leave it in terms of u. To put it back in terms of x, well, we just go up to our little dictionary here. U is 2x, so I can just substitute that in and write that this is equal to cosine of 2x. So we've done it. We started with this function, the product of sine and cosine, and we took its derivative with respect to x. We get cosine of 2x, and of course, since you are a master of the double angle identities, when you see that, you're reminded, if I needed to, I could always rewrite that as cosine squared x minus sine squared x, because that is my double angle identity for cosine. But there's no need to do that here. This is a simpler, cleaner expression. This trick we've just done, not the trigonometric trickery, but the core of taking the derivative, where we had this sine of 2x, a composite function, a function of a function, like here, the sine of the doubling function. And we found the derivative of that composite function by introducing this new variable u as a stepping stone, and then factoring the derivative into two stages. That trick comes up all the time. We will eventually be using it without even thinking about it. I give you a few examples in the section that we're doing in the book right now, in the homework, just to get used to it. We'll meet it formally a few sections down the road by its official name, which is the chain rule, after this chain of functions here, but it's easy to use once you get the hang of it. Eventually, at the end of Chapter 2, we'll work on getting to the point where we can carry out this chain rule in our heads, but for now, please do write everything out. Write y is a function of u, which is a function of x, factor the derivative, and then write everything down. Okay, as always, we've covered a lot, so it's time to stop.